welcome to all of you for today's lecture. Today we are going to look at electrophilic substitution reactions on Pyrrole and Thiophene. So we have seen that in case of 5-membered heterocyclic systems, the preferred substitution occurs at carbon number 2 or 5. If 2 is blocked, 5 is available. If 2 and 5 is blocked, then in that case it will go to either 3 or 4. So depending upon substitution, the orientation of the incoming electrophile will be governed by the substituent which is already present on the 5-membered ring. So let us start with the first example, that is Pyrrole is treated with nitric acid and acetic anhydride. Now in this case, the actual electrophile, we have seen that it is going to be the acyl nitrate. This is the actual electrophile, and then the double bond from this attacks here, and then acid oxy groups goes off, which eventually becomes a conjugate base and will help in the abstraction of proton. So quickly, if we want to show this, we can show it. Either you involve lone pair or not, but that is how it will happen. So it will be NH, and then it will be N double bond O minus, proton is there, it becomes plus, then acid oxy can abstract this proton, sorry, not here, this is 2 position is substituted. So 2 position is this one, so this becomes electropositive, and subsequently you can show the delocalization and all. This is acidic proton, can be abstracted by acid oxy group, and this is the simplest way by which you can show the nitration at 2 position. So this is major compound. The alternative thing we have seen that lone pair involvement, and then you have to show, and finally the rectification of positive charge on nitrogen, that should be the end. So that is how the aromatic sextate is restored or it is written. So that is about the first thing. The nitration, 2 nitro is major, 3 nitro would be minor product. So first one forms in 50% yield and meta would be 15%, so that is going to be minor compound. The same is true with thiophene also. Here also we will be having substitution at either 2 or 4, 5. They are the preferred position. The mechanism remains same. If you talk about the relative reactivities, then Pyrrole is going to be more reactive than Pyrrole. Pyrrole is going to be more reactive than Thiophene. Thiophene is going to be more reactive than benzene towards electrophilic substitution. Okay. So this is more or less same. The substrate is different. Now here in this case, we get this substitution. So this is meta with respect to COH. Now COH is meta orienting, the sulfur is orthopara orienting. So the cumulative effect is the Br is coming here. The reaction mechanism is like we have, so this is acetic acid, and this kind of hydrogen bonding would be there. So this will make this as electropositive, this as electronegative end, and ultimately what happens is the COH will keep, and then this double bond will attack here, and then eventually what happened is you get Br here, this will be plus COH, and ultimately this proton is sacrificed. so that this product is formed. The orientation is governed by COOH, this is meta orienting, and sulfur also function as a orthopara directing group. In this case, it orients the incoming electrophile at ortho position, the immediate position which is there. So it is cumulative effect of COOH group and sulfur of thiophene ring, so that the Br comes at only one position, that is meta with respect to COOH and ortho with respect to sulfur. Okay. Moving on to the next, this chlorothiophene is giving the major product, this ortho product with respect to this and para with respect to this. So this is ortho para, this is ortho orienting. So naturally this combination would give the same intermediate, and then the only change is the attacking double bond will be this one, and then the re-hermetization would furnish this compound. The orientation is governed by both sulfur as well as Cl. Okay. Moving on to the next one, this 2-nitrothiophene is treated with nitric acid. You get two products, 44% and 56%. Now 56% is slightly higher because this NO2 which is already there on the substrate is meta orienting, so that is major product, and ortho para orienting, para with respect to this and ortho with respect to this is going to be 44. So substantial product is there, but this is going to be major, this is going to be minor. Once again, nitric acid is the only reagent to generate the nitronium ion, and we can easily write down in which one molecule of nitric acid functions as an acid, the other functions as a base, and eventually you can generate the nitronium ion. The concentration would be less, but this condition is necessary because once you introduce NO2 group onto the aromatic ring, the reactivity of this ring goes down. So that's why here you can see that the moderate condition is there, acetic anhydride, and so acetyl nitrate is formed. Here we are generating nitronium ion from the nitric acid, and therefore the condition is optimized 0 degree, not this combination, and plain nitric acid is giving this combination of product. Then this 3-formyl thiophene subjected to silver oxide. So this is simple oxidation reaction, aldehydes oxidized to acid. So this is oxidation reaction practically. Then next one is the Ehrlich reagent. So the second or 5 position, it interacts with the aldehydic CHO and you get the adduct, the dehydration takes place, and here this compound is highly colored, so you can find out this kind of condensation reaction, and that becomes a test for this kind of compounds. Then 2-methyl thiophene, nitric acid, acetic anhydride, you get two products, para with respect to this and ortho with respect to this, because this is ortho para orienting group. So you get both the products as a matter of orientation, which is governed by the methyl group over there. So the mechanism remains same. The next one is this is Vilsmeier-Haack reaction. So this NN-dimethyl formamide POCl3 and then followed by aqueous carbonate workup. So you get this is Vilsmeier reaction. So you have to generate the electrophile in situ from this combination, DMF formyl chloride, this POCl3, and then the active electrophile is going to be different. You can show this if I show it this way, POCl3, you can show it like this. This attacks here, Cl should come here, so it will be HCOPOCl2 NMA twice and then Cl. Then this is one thing, and then this comes back, this goes off. So it will be HCCl NMA twice. So this is the actual electrophile. And then the next step is the attack of this Pyrrole ring onto this electrophile. So let me put the electrophile as HCCl NMA2. Now this is plus. So naturally when this attacks, it will take the electron flow in the direction of, and this will be positive CH-Cl NMA twice, and then naturally the hydrolysis will give us hydrolysis and rearomatization, of course, minus H plus also I will join along with this. You will have geminal diol eventually, and this will undergo loss of water, so that you get target molecule. So that is Vilsmeier-Haack reaction. The workup is done with aqueous sodium carbonate or potassium carbonate. So that is the overall reaction. So that is Vilsmeier-Haack reaction, a formylation of aromatic substrate with DMF POCl3. That is the combination what we normally use. Okay, then this one 2-nitropyrrole acetic anhydride. This is conventional nitrating agent because pyrrole is labile to strong acidic conditions, so you need to use this combination. There are two products. This is governed by NH, orthopara directing, and the second is governed by NO2. So NO2 is meta orienting. I will just mention here. This is meta orienting, this is ortho or para orienting. So ortho position is available, so that's why you get two different products. And next one is sulfonation. These two positions are blocked, so the sulfur trioxide being the electrophile, so it will be like this, O minus, and then pyridine is there. Then whatever substrate you have, the driving force is this is nitrogen. The substitutions are there, so naturally this will attack here, opens up during this kind of reaction. The charges, the positive charge on nitrogen is cleared off, and then you get SO3 minus, and then pyridine can abstract this proton, and you get the product. The role of pyridine is to help in the aromatization reaction, and this also provides a milder reagent for sulfonation, because pyrrole, the concentrated sulfuric acid, may not be very good reagent for sulfonation, especially in the labile substrates like pyrrole and furan. For thiophene one can use, but for these two you cannot use because they are labile to mineral acid. We will see some theory based problems also maybe in next lecture, where we will talk more about the utility of the reactivity of these three compounds, and then the selection of the reagents also. Now this 2-ester of the pyrrole, bromine acetic acid, once again this is meta orienting, this is orthopara, so that's why we get the two products are obtained, and that is mainly because of the orientation which is governed by the withdrawing group as well as the NH. NH is normally the orthopara orienting group, a donor, and that is how you get different product proportions. Two products are formed instead of one. So orientation difference is there. The substrates are different. NH is also functioning. This is also functioning. So we get a combination of those two products. Okay. That's all for today. Next time we'll talk more about the furan ring, the examples, and then If time permit, we'll see the theory problems also, where we'll be talking more about why one is acidic, the other one is basic, why one is reactive, the other one is less reactive, and so on. So all theory based problems also we'll try to solve in the next lecture. Okay, thank you very much.